The history of mathematics is nearly as old as humanity itself. Since antiquity, mathematics has been fundamental to advances in science, engineering, and philosophy. It has evolved from simple counting, measurement and calculation, and the systematic study of shapes and motion of physical objects through the application of abstraction, imagination, and logic to the broad, complex, and often abstract discipline we know today. From the notched bones of early men to the mathematical advances brought by the settled agriculture in Mesopotamia and Egypt, and the revolutionary development of ancient Greece and its Hellenistic Empire, the history of mathematics is a long and impressive one. The East carried on the baton, particularly China, India, and the medieval Islamic Empire, before the focus of mathematical innovation moved back to Europe in the late Middle Ages and Renaissance. Then, a whole new series of revolutionary developments occurred in the 17th century and the 19th century. Europe, setting the stage for the increasing complexity and abstraction of the 19th century mathematics, and the final and audacious and sometimes devastating discoveries of the 20th century.
Follow the story as it unfolds in this series of linked sections like as chapters of a book. Read the human stories behind the innovations and how they are made and sometimes destroyed, the men and women who devoted their lives to the story of mathematics.
As early as 6000 BCE, the early Egyptians settled along the fertile Nile Valley and began to record the patterns of lunar phases and seasons for agricultural and religious purposes.
Pharaoh surveyors used measurements based on body part in 3000 BCE. Early in Egyptian history, the Pharaoh surveyors utilized measurements based on body parts to measure land and buildings. For an example, a palm was the width of the hand, a cubit was the measurement from elbow to fingertips, and the decimal numeral system was devised based on our 10 fingers.
The Egyptians are believed to have introduced the first completely form-based time numeration system as early as 2700 BCE and probably much early. However, because there was no concept of place value, bigger numbers were difficult to manage. Although a million required just one character, a million minus one required 54 characters.
The oldest mathematical text from ancient Egypt discovered so far is the Moscow Papyrus, which dates from the Egyptian Middle Kingdom around 2000 to 1800 BCE. The Moscow Papyrus contains 25 mathematical problems. It shows an illustration with an example to find the volume of a truncated pyramid. Vladimir Golenishev bought the Moscow Papyrus in between 1892 and 1893.
The Rhind Papyrus, which dates from around 1650 BCE, is a form of arithmetic and geometry instruction manual that includes clear illustrations of how multiplications and division were done at the time. It also provides evidence of additional mathematical knowledge, such as unit fractions, composite and prime numbers, arithmetic, geometric and harmonic means, and how to solve first-order linear equations as well as arithmetic and geometric series.
The Berlin Papyrus, which dates from around 1300 BCE, shows that ancient Egyptians could solve second-order algebraic equations. The Berlin Papyrus contains a problem stated as the area of a square of 100 is equal to that of two smaller squares. The side of one is 1/2 plus 1/4 the side of the other.
During Egyptian period, multiplication was achieved by a process of repeated doubling of the number to be multiplied on one side and of one on the other. Essentially, a kind of multiplication of binary factors similar to that used by modern computers. During Egyptian period, multiplication was achieved. This effectively made use of the concept of binary numbers over 3,000 years before Leibniz introduced it into the West, and many more years before the development of the computer was to fully explore its potential. The Egyptians approximated the area of a circle by using shapes whose area they did know. This gives an effective approximation of pi accurate to within less than 1%.
The pyramids themselves are another indication of the sophistication of Egyptian mathematics, setting aside claims that the pyramids are first known structures to observe the golden ratio of 1 is to 1.618. There is certainly evidence that they knew the formula for the volume of pyramid, which is the 1/3 times the height times the length times the width, as well as of a truncated or clipped pyramid.
They were also aware, long before Pythagoras, of the rule that a triangle with sides 3, 4, and 5 units yields a perfect right angle. And Egyptian builders used ropes knotted at intervals of 3, 4, and 5 units in order to ensure exact right angles for their stonework.
Sumerian Babylonian mathematics. Sumer was an ancient civilization founded in the Mesopotamia region, or also called Iraq in the modern day. They were believed or considered as the creators of civilization as modern humans understand it. Why? It is because Sumer was the birthplace of writing, the wheel, agriculture, the ark, the plow, irrigation, and many other innovations, and is often referred to as the cradle of civilization. Why again? It is because this is where the earliest civilization started, and relatively, they are abundant to access to water. The people in Sumer or the Sumerians developed the earliest writing system, a pictographic writing system, also known as cuneiform script, where they use wedge-shaped characters inscribed on a baked clay tablets. And this means that we actually have more knowledge of ancient Sumerian Babylonian mathematics than of early Egyptian mathematics. Indeed, we even have what appear to school exercises in arithmetic and geometric problems. Sumerian mathematics initially developed largely as a response to bureaucratic needs when their civilization settled and developed agriculture. That is around 6 millennium BCE. It's for the measurement of plots of land, the taxation of individuals, etc. In addition with that, the Sumerians and Babylonians needed to describe quite large numbers as they attempted to chart the course of the night sky and develop their sophisticated lunar calendar. Take note, they were the first people to assign symbols to group of objects in an attempt to make the description of larger numbers easier. They moved from using separate tokens or symbols to represent the shapes of wheat, jars of oil, and so many more, to the more abstract use of a symbol for specific numbers of anything. Starting as early as the 4th millennium BCE, they began using small clay cone to represent 1, a clay ball for 10, and a large cone for 60. Over the course of the 3rd millennium, these objects were replaced by cuneiform equivalents so that numbers could be written with the same stylus that was being used for the words in the text. Sumerian and Babylonian mathematics was based on a sexagesimal or base 60, a numeric system which could be counted physically using the 12 knuckles on one hand, the 5 fingers on the other hand. Unlike those of the Egyptians, Greeks, and Romans, Babylonian numbers use a true place value system, where digits written in the left column represented larger values, much as in the modern decimal system, although of course using base 60, not base 10. Why use base 60? Why did they use base 60? Many different theories explain why they use base 60. One of them is that 60 has many different factors, like 2, 4, 6, 5, 3. So it is easier for them to divide the grain that was sold on the Fertile Crescent. They only use 2 main symbols, this symbol and this symbol. This is so comparable to our 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So we are going to simplify the symbols. So first, the inverted triangle here. As you can see, that inverted triangle is equivalent to 1. And the arrow facing to the left, going to the left, is equivalent to 10. its place value. So let's talk about the place value here. So any of this symbol or shape, you can have any one of the 59 symbols and you will multiply it by 1. The next path here is the 60 place, wherein you will multiply 60 times to the indicated symbol. And the another one is the 60 squared or 3600 place, and you will multiply it again to the indicated symbol. And the last one is the 60 cube or 21,600 times to the indicated symbol.
The Babylonian civilization traces its roots to 4000 BCE with the Sumerians in Mesopotamia. The early Sumerians developed the earliest known pictographic writing system known as the cuneiform script. However, because of the resources were scarce, the Sumerians used the abundant valley clay as their writing material. Cuneiform is a wedge-shaped writing owing to its appearance to the stylus that was used to make it. The early Sumerians moved from using separate tokens or symbols to represent sheep of wheat, jars of oil, etc., to the more abstract character for specific number or anything. As early as 4000 BCE, they started using a plain cone to represent 1, a clay for 10, a sizable cone for 60, and etc. However, these items were replaced by cuneiform equivalents in 3000 BCE so that numbers could be written using the same stylus used for the words in the text. The famous Plimpton 322 clay tablets dating about 1800 BCE suggest that Babylonian may have known the secret of right-angled triangle many centuries even before the Greek Pythagorean. The tablet appears to list 15 Pythagorean triangles with whole number sign, although some claim that they were academic exercises and not indicators of Pythagorean.
Greece was sophisticated enough to learn from the cultures it conquered as it expanded over Asia Minor, Mesopotamia, Egypt, the Levant, and beyond. Mathematical elements were borrowed from both the Babylonians and Egyptians, which was true of everything else as well. However, they quickly began to make significant contribution of their own, and for the first time, individual efforts may be recognized. A major change in mathematical theory had taken place in Greek society by the Hellenistic period. Euclid, also known as Euclides, was the most prominent Greek mathematician who lived in Alexandria, Egypt around 300 BCE and is best known for his book on geometry, The Elements. Attic or Herodianic numerals, the ancient Greek numeral system, had been fully developed by 450 BCE and it may have been in regular use as early as the 7th century BCE. To represent different numbers, they used symbols for 1, 5, 10, 50, 100, 500, and 1000 that were repeated until the desired number was reached. This was similar to the Egyptian base 10 system and even closer to the later Roman one. The symbols ones, tens, 100s in the numbers to be added were totaled separately, and multiplication was a time-consuming procedure based on repeated doublings of the numbers. Division was based on the inverse of this process. Squaring of the circle, the doubling or duplication of the cube, and the trisection of an angle are the three early Greek geometrical problems that can be solved with only a straight edge and a compass. These intractable problems had a significant impact on future geometric theory and led to several important discoveries, but the solutions or proofs of their impossibility didn't arrive until the 19th century.
Islamic mathematics. The Islamic Empire fused the mathematical developments of both Greece and India. Muslim artists discovered all the different forms of symmetry that can be depicted on a two-dimensional surface. Muhammad al-Khwarizmi, a Persian mathematician, contributed his strong advocacy of the Hindu numerical system 1 to 9 and 0 in the 19th century. Al-Khwarizmi's other important contribution was algebra. He introduced the fundamental algebraic methods of reduction and balancing and provided an exhaustive account of solving polynomial equations up to second degree. The 10th century Persian mathematician Muhammad al-Karaji introduced the theory of algebraic calculus. He was the first to use the method of proof by mathematical induction. Al-Karaji used mathematical induction to prove the binomial theorem. A binomial is a simple type of algebraic expression which has just two terms which are operated by only addition, subtraction, multiplication, and positive whole number exponents. Some 100 years after Al-Karaji, Omar Khayyam generalized Indian methods of extracting square and cube roots to include fourth, fifth, and higher roots in early 12th century. The 13th century Persian astronomer, mathematician, and scientist Nasir al-Din al-Tusi was the first to treat trigonometry as a separate mathematical discipline, distinct from astronomy. He gave the first extensive exposition of spherical trigonometry, including listing the 6 distinct cases of a right triangle in a spherical trigonometry.
Indian mathematics and mathematicians. Despite developing quite independently of Chinese and probably also of a Babylonian mathematics, some very advanced mathematical discoveries were made at a very early time in India. Mantras from the early Vedic period before 1000 BCE invoke powers of 10 from 100 all the way up to a trillion and provide evidence of the use of arithmetic operations such as addition, subtraction, multiplication, fraction, square, cubes, and roots. As early as the 8th century BCE, long before Pythagoras, a text known as the Sulba Sutras or Sulva Sutras listed several simple Pythagorean triples as well as a statement of a simplified Pythagorean theorem for the sides of a square and for a rectangle. The sutras also contain geometric solution of linear and quadratic equations in a single unknown and give remarkably accurate figure for the square root of 2, obtained by adding 1 plus 1/3 plus 1 over 3 times 4 minus 1 over 3 times 4 times 34, which yield a value of 1.4142156, correct to 5 decimal places. As early as the 3rd or 2nd century BCE, Jain mathematicians recognized 5 different types of infinities: infinite in one direction, in two directions, in area, infinite everywhere, and perpetually infinite. Ancient Buddhist literature also demonstrates a prescient awareness of indeterminate and infinite numbers, with numbers deemed to be 3 types: countable, uncountable, and infinite. Like the Chinese, the Indians early discovered the benefits of a decimal place value number system and were certainly using it before about the 3rd century CE. They refined and perfected the system, particularly the written representation of numerals, creating the ancestors of the 9 numerals that, thanks to its dissemination by medieval Arabic mathematicians, we use across the world today, sometimes considered one of the greatest intellectual innovation of all time. Earliest recorded usage of a circle character as number 0. The earliest use of a circle character for the number 0 was in India. The ancient Hindu symbol of a circle with a dot in the middle, known as Bindu or Bindu, symbolizing the void and the negation of the self, was probably instrumental in the use of a circle as a representation of the concept of zero. The Indians were also responsible for another hugely important development in mathematics. The earliest recorded usage of a circle character for the number 0 is usually attributed to a 9th century engraving in a temple in Gwalior in central India. But the brilliant conceptual leap in included 0 as a number in its own right is usually credited to the 7th century Indian mathematicians Brahmagupta or possibly another Indian, Bhaskara I. Even though it may well have been in practical use of centuries before that, the use of a zero as a number which could be used in calculation and mathematical investigation would revolutionize mathematics. Brahmagupta established the basic mathematical rules for dealing with zero. 1 plus 0 equals 1. 1 minus 0 equals 1. And 1 times 0 equals 0. The breakthrough which would make sense the apparently nonsensical operation 1 divided by 0 would also fall to an Indian, the 12th century mathematician Bhaskara II. The so-called Golden Age of Indian mathematics can be said to extend from the 5th to 12th centuries, and many of its mathematical discoveries predated similar discoveries in the West by several centuries, which has led to some claims of plagiarism by later European mathematicians, at least some of whom were probably aware of the earlier Indian work. Certainly, it seems that Indian contributions of mathematics have not been given due acknowledgement until very recently in modern history.
The Golden Age Indian mathematicians have made fundamental advantage in the theory of trigonometry. Trigonometry deals the study of triangles, angles, and trigonometric functions, which is first developed by the Greeks. The Indians use ideas like the sine, cosine, and tangent functions to survey the land around them, navigate the seas, and even chart the heavens. Indian astronomers use trigonometry to calculate the relative distances of the Earth and the Moon and the Earth and the Sun. Although the Greeks had been able to calculate the sine function of some angles, the Indian astronomers wanted to be able to calculate the sine function of any given angle. The Surya Siddhanta is a text that made by unknown authors and dating from around 400 CE. This contains the root of modern trigonometry, including the first real use of sines, cosines, inverse sines, tangents, and seconds. Now let's proceed on the most noticeable mathematician in this era. It's no other than Aryabhata. Aryabhata is an Indian mathematician and astronomer that produced categorical definitions of sine and cosine. He also specified complete sine and versine tables in 3.5 degree interval, from 0 degree to 90 degree, to an accuracy of 4 decimal places. He also demonstrated solutions to simultaneous quadratic equation and produced an approximation for the value of pi, equivalent to 3.1416. He also correctly believed that due to Earth's rotation, we have day and night time. He seems to have been aware that pi is an irrational number and that any calculation can only ever be an approximation, something not proved in Europe until 1761. Infinity is the reciprocal of zero. Bhaskara too is the one of the most noticeable mathematicians in the 12th century in India. He explained the misunderstood operation of division by zero. He noticed that dividing 1 into a fraction will get a whole number answer. Also, by dividing 1 into smaller fraction, it yields a larger and larger of numbers. For example, 1 divided by 1/2 is 2. 1 divided by 100 is 100. 1 divided by 1000 is 1000, and so on. But dividing 1 by 0 would yield infinity. Therefore, Bhaskara indicates that 1 divided by 0 is equal to infinity.
The simple but efficient ancient Chinese numbering system, which back to at least 2nd millennium BCE, used small bamboo rods arranged to represent the numbers of 1 to 9, which were the places in the columns representing units, tens, hundreds, thousand, and etc. It was, therefore, a decimal places value, very similar to the one we use today. Indeed, it was the first such number system, adopted by Chinese over 1,000 years before it was adopted in the West, and it what made even quite complex calculation very quick and easy. Written numbers, however, employed the slightly less efficient system of using a different symbol of tens, hundreds, thousand, etc. This was largely because there was no concept or symbol of zero, and it was had the effect of limiting the usefulness of the written number in the Chinese. The use of abacus is often thought of as a Chinese idea, although some type of abacus was used in Mesopotamia, Egypt, and Greece, probably much earlier than in China. There was a persuasive fascination with the numbers and mathematical patterns in ancient China, and different numbers were believed to have a comic significance. In particularly, magic square of numbers where each row, column, and diagonal added up the same total, were regarded of having great spiritual and religious significance. The Loshu square and order 3 square where each row, column, and diagonal adds up to 15. Perhaps the earlier of these dating back to around 650 BCE. The legend of the Emperor Yu discovered the square on the back of the turtle. It is said of taking place in about 2800 BCE.
Early Chinese method of solving equations. Ancient China developed a very efficient system of computation by physically manipulating counting, and the main thrust of Chinese mathematics developed in response to the empire's growing need for mathematically competent administrators. A textbook called Jiayu Shang, Xuanshu are 9 chapters on the mathematical art written over a period of time from about 200 before Common Era onwards. Probably by a variety of authors, became an important tool in the education of such a civil service, covering hundreds of problems in practical areas such as trade, taxation, engineering, and the payment of wages. It was particularly important as a guide to how to solve equations, the deduction of an unknown number from other known information using a sophisticated matrix-based method which did not appear in the West until Carl Friedrich Gauss rediscovered it at the beginning of the 19th century and which is now known as Gaussian elimination. The Chinese remainder theorem. The Chinese went on to solve far more complex equations using far larger numbers than those outlined in the 9 chapters though. They also started to pursue more abstract mathematical problems, although usually couched in rather artificial practical terms, including what has become known as the Chinese remainder theorem. This uses the remainders after dividing an unknown number by a succession of smaller numbers, a technique for solving such problems initially posed by Sun Tzu in the 3rd century Common Era and considered one of the jewels of mathematics, was being used to measure planetary movements by Chinese astronomers in the 6th century Anno Domini, and even today it has practically uses such as internet cryptography. By the 13th century, the golden age of Chinese mathematics, there were over 30 prestigious mathematics schools scattered across China. Perhaps the most brilliant Chinese mathematician of this time was Qin Jiayu Shao, a rather violent and corrupt imperial administrator and a warrior, who explored solutions to quadratic and even cubic equations using a method of repeated approximations very similar to that later devised in the West by Sir Isaac Newton in the 17th century. Qin even extended his technique to solve, albeit approximately, equations involving numbers up to the power of 10. Extraordinarily complex mathematics for its time.